All right, welcome back to the afternoon sessions. Yay. Um, I did notice when I looked at syllabus, actually, I had the test originally scheduled for the afternoon and lecture in the morning. Obviously, we didn't do that. But I think there's one more test that does fall on that schedule. And so when we get to that point, if you guys would rather take the test in the afternoon and be done, and maybe the Denver or the Colorado guys will be more awake and will be more awake, we can do that, but we'll see when we get closer to that. So just to give you a sort of an idea of what is left, um, we have chapter 12, chapter 13, and so those are the two chapters that we have left. So in both cases, we're going to be looking at functions of multiple variables, so functions of several variables. Often they will look like, instead of writing f of x, we will write y equals f of x, we'll write z equals f of x, y. And you can have that's two independent variables and one dependent variable, so x and y can change and you can figure out what z is. And anytime that happens, you'll have x directions and y directions. So right off the bat, well, today we're going to go back to the very beginning, and like 12.1 is, well, start from the beginning. So what can I actually plug into this function, and what do I get out? So the fancy words, domain and range, as well as just sort of general plots. And now it's going to be 3D or even worse, so that's going to be difficult to do. And then the rest is like, well, what do you do with calculus in that point? So 12.1 is basically limits, the notion of what does it even mean to be continuous anymore? Can we still do that? That's 12.2. 12.3 is, I should have this in front of me, but 12.3 is on, well, so what do you mean by derivative anymore? So when you're talking about slope and rate of change and all of that stuff in 3 dimensions or higher, what does that actually mean? 12.4 is kind of we've done this before, I think, in Calc 2, Calc 1 maybe, something called a differential, which is good for approximating. If you guys have ever had Colonel Sullivan, he always likes to say, at least he tells me he likes to say, linearize, because everything goes from complicated to easy, and so differential is on that sort of linearization process. 12.5 is on continuing derivatives. It's actually kind of a tricky one that's just based on has its own section. So how do you do chain rule? 12.6 is you don't have just one kind of derivative, you have many, and so there's something called the directional derivative. 12.7 is on tangent, not tangent height anymore, but tangent planes. And then finally, I ran out of room, but 12.8 is on optimization. So how do you do max and min and all of that sort of stuff? And then in chapter 13, and I'll just say all of that in chapter 13 is basically, instead of just doing one integral, sometimes we'll do 2 integrals, sometimes we'll do 3. That's right. You definitely should shake your head on that one. It's basically these last 2 chapters. Let's take Calc 1 and Calc 2 and just give them both steroids and see what happens. So you got to be good at Calc 1 and 2, I suppose. So, but it's the afternoon session, so let's just go back and look at chapter 12, section 1 here, which is on basic definition. And if you haven't heard already, I'll have to warn you, my son is heavy duty into Rainbow Six Siege, so you might be hearing some chatter. He said he wouldn't scream too much, but anyway. doesn't work, I'll just tell them to be quieter, I guess. Okay, so let's see if or I'll just talk louder. So up to this point, so this is just introduction to functions of several variables. So before, this is sort of the old stuff, remind you, we would just say y equals f of x, and you've got two variables, x and y, but this x is called the independent variable, which just means it's allowed to take on whatever value you want. And then once you know what that x is, you can get y, or you'll get y, because you have to plug it into the function and you'll get y out. And that's called the dependent variable. So we're sort of wondering what the difference is. Well, that's it. I mean, one variable allows, it can move around, that's called independent, and then the other one will depend on that particular value. What values can you actually plug into x? Well, some functions you can plug in any x you want, like a polynomial, trig function, you can plug in anything you want. But a square root, or a natural log, or a reciprocal or something, could be, you might have restrictions on this, and so this is where we use the word domain. And so this is all the x values, all the allowable, you can think about that way, all the allowable x values. And so if you think about this, these are real values, and if you've never seen this symbol before, it's a capital R with this funny little extra line on it. So that's called the set of real numbers. I think you probably have seen that before. So it's a set of all real numbers. The domain, the fancy thing here, is you say it would be a subset. It is your little subset notation. It could be all real numbers. If it's a square root, it would be all numbers that were not negative, so 0 and positive numbers. If it's a reciprocal, then it would be everything except 0, so you can't divide by 0. And so typically what this is this is a collection of intervals. So it could be infinite intervals. Could be the whole real line. It could be only a restricted small portion of that. And then the range is it's all of the resulting y-values. So you just take all the values in the domain, plug them into your function, and then whatever comes out is the range. And this is also going to be a subset of the real numbers. So it's going to be intervals or all real line, the whole real line, or something like that. So we've seen a lot of this before. Just for example, if we said y equals the square root of 1 minus x squared. Let's do a basic example of that. If you wanted to know, so we'll probably write D for domain, R for range here. Then the domain on this one is, well, we know that x can't be too big, because if we plugged in like 5, this would be 1 minus 25, and that's not going to work because it's a square root. We also couldn't put in negative 5 either, because you square that, and you got to square it first, so it'll be 1 minus 25 again. So that's no good. So it can't be like too big, either big on the positive side or big on the negative side. In fact, the only numbers that work here is that x has to be between -1 and 1. Those are the only numbers you can plug in. Everything else is going to cause a negative under the square root. So the domain, you could say something like this. You could say that x has to be between 1 and -1. So you can write it in interval notation, like that. I know it's kind of funny that you have two of these less than or equal, but it just means you read left to right. Everything where x is greater than or equal to -1 and less than -1 simultaneously. If you prefer, you can write it in interval notation as -1 to 1, and we put these brackets to say that the endpoints are included. You can plug in 1, because you'd have the square root of 1 minus 1, which would be 0, and that's perfectly fine. So those are the allowable values. That's called the domain. The range of this is, well, what y values can you possibly get out? And this is a little more difficult to know exactly what values. But you start plugging things in and realizing what ends up happening is, you can get 0. If you plugged in 1 for x, you would get 0. But you can't get any negative numbers because the square root means the positive square root. So you know that at least the y values have to be greater than or equal to 0. Now, how about on the high end? Is there any restriction on the high end? And you're like, I don't think so. But then you start plugging these things in and you realize as x gets closer and closer to 0, then the largest the y can be is 1. You can't get above 1 in this. And so we would say that the range is all the y values between 0 and 1. So you could just plot it, right? I mean, maybe you recognize this one already. It's like, yeah, that's just a semicircle. So you know that x can only be between -1 and 1. So the domain is on the x-axis. How big can y be? It can only go up to 1. So that means that the range is the y is only between 0 and 1. So you look left to right for the domain and up and down for the. So again, that hopefully is all review, but it's not bad to review this stuff, especially because it's going to get a little more complicated. Okay, so now the new stuff. So Z is typically the next letter we use is some function of x and y. So x and y are the independent variables. We now have 2 independent variables. And we still have 1 dependent variable. Okay, so we're going to basically going to plug in 2 numbers here and get 1 number out. So the domain of this is now, it's not plugging in numbers, you're plugging in 2 numbers simultaneously. So really, it's the set of all allowable pairs of numbers, x, y. It's not like, yeah, so in the previous one you plugged in 1 number and you looked at how many of those you could plug in. Now you have to figure out which pairs you can plug in. So automatically this gets a little more complicated. Where is this in? Well, if you're looking at pairs, x, y, these are all the numbers in the xy plane. So this is a subset, use that symbol again, of the xy plane. And so these are no longer intervals anymore. These will be like, so to be made up of like regions in the plane. It could be circles or squares, or it could be an entire plane. It could be half the plane. So they're not intervals anymore. So that's tricky. And not only that, the XY plane, I think sometimes books will write it like this. It's R in one direction and R in another direction. So they'll put R with a superscript to represent real numbers in both directions. So that's the XY plane. So it's all the possible pairs you can stick in. Then the range, well, these are the resulting Z values. And so those are just real numbers. This will be it'll be a subset of the basically Z-axis. So you can think about it, these are real numbers, but it's really just a subset of the Z-axis. Maybe 0 to 5 or something like that. So, for example, let's put the right one down here. For example, we could do Z equals E raised to the 1 minus x squared minus y squared. E's been feeling left out, so we got to put it on. So what values can we plug in and what values do we get out? So the domain is the XY pairs that we can plug in. So we'll look at this. What restrictions are there on plugging in values for X and Y? Well, I can plug in 0 and 0. And that would be fine. I get e to the 1. I can plug in 1 and 1. I can plug in -1. I can plug in square roots. I can plug in any number I want. It's not going to cause me to have division by 0 or weird square roots or bad natural logs or something like that. So the domain here, as you would say, it's all XY pairs. And that's one way to write it. The other way is to say it's the, if you don't like to write that, you can say it's the entire XY plane. And the real shorthand, I don't like doing it very much, is you would just say R2. So that's just shorthand for this. But every time you do shorthand, you run into problems. So I'll try and not do that. You just might see it. So I can plug anything in that I want. Now, what about the range? Well, let's see. If you start plugging in some numbers, you could see what kind of z values you might get out. So if I plug in 0, 0, let me just plot a couple points here. We'll plot the whole thing in a second. But I plug in 0 for x and 0 for y, I'll get e to the 1. So I'll plug it in and get 0 squared, subtract, I'll get e to the 1. Okay, so I know I can get that. If I plug in, say, 1, 0, if I plug in 1 for x and I plug in 0 for y, I'll have e to the 1 minus 1, so that'll be e to the 0. That's equal to 1. So I know I can get the z values I'm trying to get, trying to figure out which ones they are. I know that I can get it 1. I can get e to the 1 or e. One other thing to note, if I plug in 0 for x and 1 for y, I get e to the 1 minus, I also get e to the 0, which is equal to 1. Oh, so I may actually end up getting the same thing out in more than one case. And so we'll get this. Now, here's a question. What value of x and y do I plug in to get 0? How do I get 0? By plugging in numbers into e here. So let's look at that. 0 would have to be e to the 1. Okay. So how do you solve an equation that looks like that? Well, in order to get rid of e, you really would like to take the natural log of both sides. And that's a problem, because we would end up with a form that looks like natural log of 0 equals 1 minus, it gets rid of the e and get to this. The problem is that natural log of 0 is undefined. So what that means is there are no values of x and y I can plug in to make this work out. So that means that 0 will never be in the range. It will never be in the range. In fact, no negative values will ever be in the range either. Because if you tried to solve, if I wanted to get -1 out, I'd have to set this curve equal to -1. And then to solve it out, I have to take natural log, and I can't take natural logs of negatives either. So up here in the range, I know for sure that z can't be negative. So I write for sure that z has to be greater than 0. Now, what about on the high end? So let's see. Can I get? Can I get? Pick a value up here. Can I get z equal to e squared, for example? I could put in a number like 3 or 5 or something like that. I'm going to have to do a natural log, and I don't really want to do that yet. So can I get this value out? So let's try. Let's set z to be e squared and they're equal to my function. So e to the 2 equals e to the 1 minus x squared minus y squared. So if I could do that, then e to the 2, e to this, the powers would have to be the same. So I could either take natural log of both sides, or I could do the power 2 would have to be 1 minus x squared minus y squared. And if you solve that, that means that x squared plus y squared would have to be -1. And I hope that you look at that quickly and go, wait, I take x and square it, and I take y and square it, and I add them together, and I get a negative number? And the answer is no, I can't do that. Because the left-hand side is positive, the right-hand side is negative. So that's not possible. So I can't get e squared out of this. In fact, you might say, well, look, how big can this possibly be? Well, if I want to make it this very big, then I've got to make sure that these numbers up here are not really negative, because if you had an e to the negative, that means they're reciprocal. Now I'm going to be even smaller than 1, and so that doesn't work. So how big can this thing possibly be is the same thing as what's the littlest I can take away. So if I looked at that, that would be 1 minus, if I factored out x squared plus y squared. What's the littlest that I could take away from 1? And the answer is the littlest I could take away is if they are both 0. So if they're both 0, then I take away the least amount from the power, which means it makes my z as big as possible. And so I know for sure that the highest this can be is when the littlest I take away is 0, and that'll be z gets e. That's around 2.7 inch, a little bigger than 2.7. So I can plug in any number I want, but the highest number I'm going to get out of this is just e, and that'll occur when x and y are 0. I already knew that one. And I can never get negative, so that looks okay. So already it's a little bit more complicated. But how do you plot this thing so that it's maybe a little bit easier to see what the domain is? And the answer is you kind of come back over here and you realize, hey, look, only 0, 0. If I plug that in, will give me an e. But if I plug in 1 and 0 or 0 and 1, I can get the same value out. How often does that thing happen? So let's see that. So, for example, how often does, for example, z equal 1 in this? If we copy it in this function here. So if you look at a plot and you did like an elevation plot and you looked at elevation 1 unit up, kind of what does the object look like at that 1 unit? So let's just set them equal to each other and see what kind of x and y we get out of this. So if we set them equal, we'll have 1 equals e to the 1 minus x squared minus y squared. Okay, so solve that out. So take natural log of both sides. If I take the ln of 1, that's 0. If I take the ln of e, well, that cancels the e part out, and I just get the power, 1 minus x squared minus y squared. And so if you just solve that, well, that gives you x squared plus y squared equals 1. So any point that causes x squared plus y squared to be 1, then when I plug it in, I'll get e to the 0, which would be 1 for z. So how many points are there where x squared plus y squared equals 1? And the answer is there's infinitely many, because that's exactly a circle. Any point on this edge here, if I took any point on the edge, plugged it into this function, squared x, squared y, that would be 1 because it's on the edge of the circle. E to the 1 minus 1 would be 0, and I would get 1. So going back to the very beginning of the last chapter, this is called a trace, or if you prefer, it's called a level curve. And so if you try to put this all into a plot that's actually in 3D, with x, y, and z, then drawing the circle down at the bottom. If I pick any point in there and plugged it into the function, they would all be up here at 1. Any point I plug in there, I will go up 1 unit and I would put a dot. So I'd go plug in XY down here in the domain, and then the range part would go up from there, and so I get this. All right, so we get that. Let's try one more of those, and then I'll show you how these things sort of come together. That you could say, well, how often is z equal to a half? What x and y values can I plug in order to get a half? And so this is just another level, elevation. So let's just try. So 1/2 would be e to the 1 minus x squared minus y squared. And we want to solve that. So let's see, I take the natural log of a half, and I'm doing that one on the fly. I'll just calculate that in the calculator here. 0.5 natural log. That is, well, let's see. So natural log of that, take the natural log of the left, take the natural log of the right, and get 1 minus x squared minus y squared. The natural log of a half is, that's approximately negative 0.0693. So if you then solve this out, it's sort of approximately x squared plus y squared is approximately, bring us to the other side, 1.693. Now, what is, so any point xy, if I plug in x and y and get 1.693, or really 1 plus the log of a half. If I stick it in, I'll get z equals a half. And what that is that's also a circle, it's just a larger circle. So the level curve for level a half is a larger circle in the xy plane. So if I put these things together here, x, y, you probably now have seen this in surveying class, or if you've done any sort of mountaineering or map reading or something, then it'll look like this. They'll draw a circle. Here's our first one, and they'll write z equals 1 next to that circle to remind you that if you're looking at a mountain, you will then come 1 unit up when you're drawing. How about this one? Well, what's the radius of this circle? The radius is approximately, okay, 1.693 square root. The radius is approximately 1.3. And so you go to 1.3, go to 1.3, you draw that circle. And you would say that level curve is z equals a half. So if you're looking at this like as a mountain or a hill, that'll be when z is a half. You can lift it up out of the board. I've already seen that in the middle, the only point that hits will occur when z is e, or e to the 1. And as I go out further and further, I get bigger and bigger circles, but the elevation is not quite as high. So I don't know if you guys are good at seeing this kind of thing, but in 3D, it looks like you start up here at e to the 1, and then I'm going to make a circle, and I'm going to make another circle, and I'm going to make another circle, and I can never hit the xy plane because I know this thing can never be 0. So it kind of does this, and it comes down on this side, and then everything is just the circle around it. And I'll kind of draw the back circle. Wrap around it. So what this thing really looks like is if you just took the bell curve and spun it turn it around so it looks like the bell curve in every direction. That's exactly what this thing looks like. And so that would be the plot using level curves or traces. If this was a weather map, you might say, well, everything in this area has temperature 1, and everything on this circle has temperature of half. In which case, the level curve, I don't know if you've done any meteorology or something. These are called isotherms. So that means the same temperature, isotherm. And so these are kind of like weather maps. Of course, you've seen weather maps on TV. They're often color-coded, and you can do this here as well. They're color-coded. But anyway, that's the idea on that. I'm going to do two more examples. See if you have questions, and then let you guys go work on homework. I do have another meeting. Unfortunately, got scheduled on top of the last half hour, so apologies for that. But maybe you're too upset with that. Okay, so for example, we won't do the whole thing out, but z equals the square root of 1 minus x squared over 9 minus y squared over 4. Okay, so we have a square root now, so we're going to impose some well, we can't plug in anything we want. We don't want the inside to be negative. So we know for sure, if we're trying to do the domain of this guy, is we must have that 1 minus x squared over 9 minus y squared over 4 can't be negative. So that's going to have to be some number bigger. It could be 0, but it can't be negative. So it has to be greater than or equal to 0. So what that means, just by moving the x and y over, that means that x squared over 9 and y squared over 4 has to be less than or equal to 1. So you have to plug in numbers x and y that make this work out. So it would have to be less than 1. And you can just try some points in here, and what you end up with is, well, what's the largest y or x could possibly be? The largest x could possibly be is 3. Because if x is 3, then this will be 9 over 9, which is 1. And the other equation, or x squared over 4, is always going to add something positive to it. If you've already hit 1, you can't add more and still be less than 1. So the largest values you can get are actually 3 and minus 3 for x. And that's when y is 0. Now, when x is 0, then the largest y could be is 2. Because if you square that, you get 4 over 4, and you're right on 1. So 2, and in fact, minus 2, because everything is squared. So the largest values going up and down are negative 2 and 2, 3 and 3 on the side. And hopefully your eye is like, okay, I've seen this before. That's actually looks like the equation of an ellipse. The only catch is what does less than or equal mean? And the answer is it means all the points inside of the ellipse. So anything that's inside or on the edge of this here, that's the domain. It's a closed-in ellipse. We've got the border and all the points on the inside. So when you plot this, that means the only thing you'll see is inside of that region. So if this is x and this is y, then we know that x is 3 and minus 3, y is 2 and minus 2, and if we plotted that region down to the plane, there will be no points outside of this area. Everything will be above this region here. I can't plug in anything too big, or else I'll get a negative in the square root. What about the range? Well, it's the same sort of idea, is I know that I can't get any negative numbers because it's a square root. I could get 0. I've already seen that I can get 0 if I plug in, say, x equals 3 and y is 0. So I'll get 1 minus 1 and it'll work. The largest value I can get is, well, it turns out to just be 1, because if I plug in 0 and 0, I'll get 1. And any other number I put in will take away from 1. So it's going to get it down. So I know that if I plug in the origin, the highest value I can get out is 1. So there's like the maximum, the minimum is 0. I'm not going to do all the level curves, but maybe not too surprising that if I change the z, take square both sides and work this out, I'm going to get a smaller ellipse. So this thing looks like at the top you get nothing, then you get a slightly bigger ellipse, then you get a slightly bigger ellipse, then you get a slightly bigger ellipse, and this thing looks kind of like the top half of a rugby ball. It's a sphere that's been sort of stretched out, but only the top half. So it's the top half of our ellipsoid. So the range of this domain. Now a weird one. We'll do this and then we'll call it a day. Oops, I don't know what I'm doing. Z equals x over x squared plus y squared. Okay. So what's the largest? What values of x and y can I not plug in? And that'll help us figure out what the domain is. So I don't want to divide by 0. So the domain will be all pairs x, y, so that x squared plus y squared cannot be 0. If I don't divide by 0. Everything else is fine. I just got to make sure I don't divide by 0 in this fraction. So what values would cause x squared plus y squared to be 0? Well, the only thing that would cause that is actually 0, 0. Because anything else squared will be positive. So it's basically all pairs except for the pair 0, 0. So you could write it like that. Sometimes they would write it as like this. All the x and y, and you probably have seen this before, but that bar means such that. X squared plus y squared is not 0. You could write it like that. You could write it as the set of x, y not equal to 0, 0. Or even shorthand, they do this. It's the entire plane, written as R2, take away the origin of 0, 0. So it's kind of like a minus symbol there. If I take away. In fact, some people just write it as R2 minus, like straight minus. Some people put it more of a slash. I kind of went in the middle. And so it's the entire plane, but not the origin. The range, well, let's see. This will actually help us with the level curve. So we want to know what are the possible z values that will come out of this. So let's just pick a z value and see if we can hit it. And if we can, then it's in the range. If it's not, then it's not in the range. So let's pick a z value, and I don't really want to use z, so let's just use like another letter. And the book uses c. So we'll be able to adjust c later and see what kinds of other things maybe. We'll see what values work. So let's set z to be c. So let's do c equals x over x squared plus y squared. Can we figure out values of x and y that when you plug them in, we get that c value out? So that's what we need to figure out. Is there any restrictions on c? So in the last problems, there were restrictions on c. In this case, let's see if we also. Let's try. Okay, so c equals x over x squared plus y squared. We can cross, well, I think the problem, maybe one thing we want to get out of the way is, can we get c equals 0? Is that a possibility? Otherwise, it's going to be a pain. I might want to divide by c at some point. So can we get c equals 0? What values of x and y can we plug in here to get 0 for c? And one value is, let's set Cx to be 0 and y. We can't let y be 0 because that would cause division by 0. Really, we can pick anything else. Because if the top is 0 of a fraction, the whole thing is 0. As long as the bottom isn't also 0. So if we plug in x equals 0 and y equals 1, then z would be 0 over 0 squared plus 1 squared, which is 0. So check. So we can get 0 as a value for z. So 0 is in the range. Got that. Now, what happens if c is not 0? And again, I'm going to probably want to divide by that. So let's see. So multiply both sides by x squared plus y squared times c equals x. Still maybe not clear what that is. So we'll do a little bit of algebra here. We get x squared plus y squared equals 1 over cx. So I'm just going to divide. And I know I can do this now because I've ruled out c being 0. So this is okay. Next step, which is maybe not as obvious, but we do want to bring this over. And this will actually help us finish the problem off with the level curve. So I'm not trying to just do algebra for algebra's sake here. I can bring that over. And actually, let me just do 2 steps here at once. So maybe this is a hint. You're like, oh yeah, okay. So if I had an x squared and an x, then what do I have to do? I have to complete the square. So I have to take half of this, so that's 1 over 2c, and then I have to square it. And I have to add that on. So if I square that, I'll get 1 over 4c squared. And if you complete the square and add something to the left, you also have to add it to the right, adding the 4c squared, 1 over 4c squared, and adding that to both sides. And the purpose of that is, therefore, I can complete the square as x minus 1 over 2c squared plus y squared equals, and I'm going to go back and go ahead and write this as 1 over 2c squared so that it gets me in my standard form. That is a circle. And the center is at 1 over 2c 0, and the radius is 1 over 2c. I suppose if you want to be real technical here, the radius is actually the absolute value of that. I need the radius to be a positive number, and c might be negative. So this is the level curve for that particular value of c, which means I can hit any c that I want. I pick any point on the circle, plug it in to the function, and z will work out to be what I need it to be. It'll work out to be c. If it's 0, then I can pick lots of points and get 0. And so let's see what happens if I'm trying to plot all of these traces. These are all the levels. I just have to pick values of c, draw the level curve, put my little isotherm or whatever you want to call it, my elevation marker on there. And so here's what it's going to end up looking like in 2D. So if c, and I just go ahead and just rewrite the equation here. So z is x over x squared plus y squared. The traces are x minus 1 over 2c squared plus y squared equals 1 over 2c squared. So, for example, if c is 1, then that is, these are all going to be circles where the center is at 0, 1/2, and the radius is 1/2. So we can draw that. Draw a circle that is centered at 0, 1/2. Crap, reversed. Again. a half 0, and radius a half. So if it's centered, here's 1. The center is there, and the radius is half. So it actually comes around and it hits the origin like that. And that is when Z is 1. So that's my elevation profile, or my isotherm, or whatever you want to call it. So that's what it's going to look like. So in 3D, if the Z is coming out of the screen at you, you'd have to lift that 1 unit up. So that's if C is 1. What happens if C is 2, for example? If C is 2, so if I wanted to go 2 units on the Z-axis, what does that look like? Well, again, it's a circle, but the center is at a quarter 0, and the radius is a quarter. So that's going to go a quarter to the center and then another quarter out here. So I would draw a little circle inside, and that is when Z is 2. Now, to draw this circle is at 1 height, and the little circle is at 2 height. That was it. All right, I'm going to draw a couple more and then draw the whole thing, and then have to color it here. What happens if C is a half? So if C is a half, now the center, and the center I plug in, I'll get 1, 0, and the radius will be 1. So that is 2. That's going to be a big circle. And that is the isotherm, or the level curve when Z is a half. Those are all positive ones. What happens if Z is C is negative? If C is negative 1, then that means you're going to go 1 unit the elevation negative, so like into the border down the Z-axis. The center is at half, negative a half 0, and the radius is a half. So it's really going to look like on the other side, same circle of radius 1, and that's when Z is Z equals negative 1. So if you were to draw this, it will be into the board. I'll try and do it on the next page, but let's see. So, and by symmetry, it turns out if you draw a little circle in here that goes through and has radius a quarter and center at negative a quarter, that is when Z is negative 2. So now it's going to look really weird at the origin. It's like this one is 2 units out, the one on the back side is 2 units down. And then maybe if I draw one more big circle here, that is going to be at level negative. So let's see if we can put all this together in a 3D picture. But all these things are sort of coming up as circles getting smaller. And this one here, they're going down, the circle's getting smaller as you go down. So if you can see this, congratulations. It's terrible. Move to a big X, V. Again, it's coming along the x-axis here. So it's going to look, I'm going to reverse these just for a second, just because so you can see it's not the right way, but it kind of looks like this. You'll have small circles coming down. They're getting bigger and bigger and bigger. So connecting this and spreading out. And then on the back side, you'll have circles that are, small circle, and then you'll have a bigger circle, and then you'll have a bigger circle, and a bigger circle, like that. And I don't think that this is in here. Let me, I think I can pull up. You can tell me if you can see this. Sometimes the screen is not viewable. So Wolfram alpha plot x, z equals x divided by x squared plus x squared plus. Here we go. So can you guys see that?
No, sir.
Ah, crap. Okay. Let's see if I can try this. Stop the share there and just do share screen. Can you see it now? Yes. Okay, cool. So these are all the level curves that we drew. They color coded it so that as they are darker, they go down, and as they are lighter, they go up. So you can see that, and that they just cut this off at a certain height. If you drew it higher, I think we can actually do this. If we said from z equals -5 to z5, let's see if they allow us to do that. Oh, that wasn't very nice. No, it doesn't. Well, that didn't work. But this one's plotted by only up to height of half and down -half. So these tubes on the screen, which I'm pointing to the screen, a bad idea. These tubes are coming up and getting smaller, and these tubes are going down. It's like a double wormhole or a double black hole or something. So anyway, that is another thing that's going to sort of take practice. And the question is, that's going to come up in the next section is like, what's really happening? What is happening as, man, my handwriting is gone today. As we get closer to 0, 0. And so we're going to introduce the idea of a limit as x, y gets closer to 0, 0. It's like a double limit. And that's 12.2. That'll be cool. Tomorrow you can dream about that tonight, I guess. So anyway, I think we'll probably stop there. Can't remember exactly what homework is due tomorrow, so look at the schedule on that, and we'll just meet again at 7:30 tomorrow morning. So, and if you have homework questions, we can just do them. So I know it's been a long day with tests and all this stuff, so go enjoy the rest of your afternoon, and I'll see you guys in the morning. Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you, sir.
See ya.